Alright, making kind of a corrections video or just a little extra clarification of the last video. So, because the event horizon and the actual surface are two different things, and so I wanted to clarify that I do know the difference between those two things. So anyway, event horizon and, okay, so this would be, say, the black hole. This is the actual mass of the black hole here. And the event horizon is out here, okay? So that it's a place in space, okay, like stated, that if I gave something a velocity of the speed of light, it would slow down to zero velocity by the time it came here, and theoretically would end up crashing back down again, just because it would stop and therefore be gravitationally influenced. So it's the place where light can't escape, so to speak, as a theoretical argument. I don't know how, yeah, that's good enough. But no light, this doesn't actually happen. Okay, if we did an experiment with light, like say the moon's out here, we put a mirror on the moon, we shoot laser beams off the earth and shoot it to the moon, and the light comes back, it'll be in a heavier, this gravity is heavier, lighter, so theoretically the trip to the moon should be slower than the trip back, because if light was being affected by gravity, I don't think they've ever demonstrated that to be a fact. I don't know exactly how they would demonstrate it to be a fact anyway, just because you'd have to time, you'd somehow have to know when the light hit the mirror on the moon, and you can't really know that time precisely because you're still stuck, it's happening the speed of light. And you need instruments that are capable of detecting things faster than the speed of light to be able to do that test. Well, anyway, they should just do it with satellites. They should put a couple of satellites up in orbit at a specific distance, and then, far enough away from the Earth, pretty far, far. And then just shoot light from one satellite to the other and see if they can bend it around the circumference of the Earth, well outside of the atmosphere or the see, that's the problem. The Earth is magnetic, and so it has a whole big, huge, giant magnetosphere around it. And again, that's, in my opinion, what's going to deflect the light. So that's another thing I wanted to be clear on. I said things like light doesn't move around corners. Light can be diffracted when it hits elements of matter, particles of matter, electrons specifically. And light is changed in its direction by that event, but light can't bend on its own. It has to be deflected. Okay, so it doesn't just seep around corners like the air pressure is just seeping around the corners. It's doing it without banging into anything per se. It's doing it by the mere kinetic bouncing off of each other. And light doesn't do that. Light doesn't bounce off of each other. It has to bounce off matter. Big difference. So anyway, back to this event horizon. So to be clear, the event horizon is also that this math works in reverse. And what this math basically means is if I take a stationary object and place it on the event horizon, no matter what it is, no matter what that object is, it will, presuming no atmosphere here, of course, it will be going the speed of light when it hits the black hole. So the actual material surface of the black hole. So the idea would be is I could put a stationary object here, the monkey, and by the time it hit the black hole, it would be moving the speed of light. So that's the inverse is true. And so another way of looking at it is like the Earth does have an event horizon. It does have a point of no return. It's just that point of return is like 10 times the size of the known universe. It's the gravity always exists. It doesn't ever die. And so it's slowly pulling, we're pulling on something very little, a little tiny bit each time. So the velocity of something that leaves the Earth, let's say, it's very slowly being degraded by a little tiny bit each second. And it just is. It's being slowly pulled back to the Earth. The whole universe is pulling towards each other. All these gravitational bodies are degrading your velocity in certain directions. A little tiny bit. And if you had this unlimited amount of time to wait, I don't know how many billions of years it would take, but yes, theoretically, Voyager or some other satellite you shoot off, if there's no other gravity to suck it up, it would slowly end up coming right back to Earth again eventually. because the little tiny tugs would all degrade its velocity away, and eventually its velocity away would be converted by the acceleration in the opposite direction. And so there is an event horizon for the Earth. It's just that it's really, 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 really far away. And so you have to understand that's how insane their condensation of mass is when they talk about black holes, because they're taking something that would be many dimensions of the universe, size-wise, and condensing into this little thing and saying there's enough mass in here to create an event horizon 3 miles away. And to create an event horizon 3 miles away, you'd have to have an insane amount of mass, insane amount of mass in a tiny amount of space. And I just don't think that's what black holes really are. I think black holes are just black suns, and suns can be pretty big, very big. I think black holes are very big, and event horizons are tricky. I'm just saying that the event horizon is, it almost has to be, in a sense, it's a gravitational location. See, I just don't know if they can get away with what they're saying. I'm just trying to think of it in terms of like relief maps, where the lines would get tighter and tighter as you get closer and closer, because it's accelerating in terms of the peak. And so the gravity is really strong here at the surface, and it gets weaker and weaker out here. So the argument would be is something could be losing 99% of its velocity by the time it reaches this point. And this last little bit it loses at this point where it freezes in space, so to speak, where it stops, where all of its velocity is absorbed. But the actual gravity at that point could be very weak. Like the event horizon for the Earth, if you think about it, like I say, let's just visualize it, 10 universes away. There's the event horizon for the Earth. That gravity is incredibly weak. When you cross that line, it's almost like nothing happens. And clearly what happens with a black hole is when you cross this event horizon, somehow I'm supposed to believe there's very weak gravity here, at the event horizon, and, you're moving the speed of light by the time you get here. And I'm saying that even by the inverse square law, this 4 times 4x, where the gravity gets 4 times stronger as you move half the distance, kind of a thing. Even with that, again, this would have to be an incredibly small mass for it to be diluted that rapidly. So that's sort of like the argument. Like as this pen gets further and further away, it almost becomes invisible. And it's like the focal length is kind of, you could argue, would be kind of defined by that mass element. And so then at what distance this gets blurry and disappears would change based on the focal length. And the focal length is, again, analogous to how much matter you're condensing into how small a space. So the inverse square law becomes kind of important if the blocking thing, this thing making the shadow, is very, very small. If I make the thing making a shadow really small, it's going to be a very weak shadow at 2 inches away, because it's only such a tiny, tiny thing. So again, that's what they've done to create this mechanism, is that they're just making up the focal length. They're just saying, well, look, to make this add up to our math, we'll just say the mass inside the black hole is 3 kilometers across. And I don't think it's accurate. But anyway, that's the argument. I mean, I just want to make that clarification that I do understand the difference between the surface and the event horizon. It's just that the event horizon is really close when you create super dense mass. So I'm just saying that all of our event horizons, the ones we understand, like the event horizon for the sun, I don't know how far out it goes, but there's probably a more realistic number for it. It might be 1 billion light years away, but it's out there somewhere. If the sun, again, if it was a clean universe and the sun was the only thing in it, its event horizon would be at some location. So it's not as far as the Earth's anyway. Probably still a long way away though. Anyway, it doesn't matter. The point I'm making is that yeah, it's just the fact that they've created this matter that we just don't see anywhere else in all the other celestial bodies. There's none of this super dense matter. And so that's what black holes, the conversation should really be about, is how does energy get consolidated? And that consolidation has to be accounted for somehow. You have to basically claim that yes, there is a super dense element. And that's what black holes are made out of, is super dense element number, whatever, 10 zillion. Give it a big number. Uranium 4,687,542. Something like that. Because that's the only way you could create that much consolidation of the substance. And it is a substance. The universe, again, is made out of substance. Mass is not an illusion. Mass, E equals mc squared. I mean, you have to account for mass. And mass is made out of energy. And so you have to say the energy's there. The substance is there. And to say that it's only occupying 3 centimeters kind of has to be explained. And I just don't think it's the accurate explanation. Black holes are big. And they're heavy, materially heavy. They're made out of probably heavy elements. But they have to be made out of an element. That's probably enough. I think they're just an illusion. I think black holes are basically donuts. So I think black holes are like this. And this donut is spinning very, very fast. Okay, this is like this. So it looks like it's a spherical object. But it's not really. It's a donut spinning. So anyway, till next time. And such. Yeah, this is all theoretical stuff, so there's no no point in getting too deep into it. But yeah, I mean, I have to see an image from a telescope. I have to go find one where they claim this black hole is 3 centimeters across. The actual black hole. I don't buy it.